Hi, BC Calc. These are your day 120 notes. Day 120 is about parametric arc length and surface area. So arc length and surface area are definitely topics we studied back in chapter 6 when we started talking about applications of integrals. And today we get to apply that and see what it looks like from a parametric equation perspective. Before we get there, from yesterday's lesson, hopefully you recall how do we find the derivative of a pair of parametric equations, x equals f of t and y equals g of t. I filled that in for you at the top here. And then the second derivative, we know we're going to compare the first derivative to dx dt here. And that's the way that we calculate the second derivative, d squared y over dx squared. All right, so with those general rules, see if you can apply that to this pair of parametrics given x equals and y equals. Find dy dx when t equals 1. And then similarly, find the second derivative there. All right, so go ahead and try those two out. Next time we see each other, we will go over those. So let's go right into the new information then. So we've got arc length of a parametric curve. Well, what we're going to do, of course, is let's compare this to what we know about arc length in general. We've done arc length with respect to x and with respect to y. And the way we derive the equation is it's something to do with distance. And it turns out we can get this simplified too. We're looking for the length from a to b along the x-axis, the square root of 1 plus dy dx squared. And that's with respect to x. If we were doing this with respect to y, we would have y bounds for c and d. We would want to get our equation as x in terms of y and find dx dy, and then be integrating with respect to y there. So hopefully those formulas look familiar from arc length. We've done arc length recently enough that maybe they do. But let's talk about what we have in a parametric world. Okay, so here's what we've got. If we want to find the length along this curve, where this is representing time 1 and time 2. Okay, how can I create an integral that represents the length along this curve that's defined parametrically from one time to a second time right here? It's going to have a very similar feel to what we have up at the top in rectangular form. We know that distance is approximately the change in x squared plus the change in y squared. But this change in x and this change in y that we're looking at have to be with respect to time, right? Because x and y are going to be defined in terms of t. So therefore, we would have the following. Okay, it's the square root of delta x over delta t squared plus delta y over delta t squared, and then times some delta t. So what we're going to do is we're going to break this up into really small amounts of time along the way from t1 to t2. We're going to find those lengths. And then, of course, if we find the sum of those lengths over that time frame, that's going to lead us towards our definite integral. Okay. But just to bring back some old notation for you in terms of a Riemann sum, if you take the limit as those widths, those delta t's go to 0 for the sum of all of your intervals from t1 to t2 for those distances, then what this amounts to in the end is that this is the limit definition for our Riemann sum that turns into the following definite integral. Okay. So this is just kind of bringing back some old notation just to refamiliarize yourself with that. But what it amounts to in the end is to find parametric arc length. We're going to do from t1 to t2, the square root of dx dt squared plus dy dt squared with respect to time. Okay, so hopefully we should be able to make a quick connection there from what we know about rectangular form and be able to, if we have a pair of parametric equations defined for us, we can go ahead and find the arc length with respect to t there. So let's actually see an example on the next page where we have the graph of x equals cosine cubed t and y equals sine cubed t. We want to see what the length of this curve is from 0 to 2 pi. In order to get us a better understanding of what this curve looks like, sometimes parametric equations you can probably visualize maybe what the rectangular form would be and therefore know what the graph looks like. But beyond that, if we're not sure what this looks like, let's actually graph it over the following window. So for my graph, I'm going to let my t values go from 0 to 2 pi according to the interval that we're given. And then we know that the possible outputs for x and y are only going to span -1 to 1 for cosine cubed and sine cubed. So it appears that if we extend that even just from -2 to 2, that's going to be an appropriate window for x and y to see the entire graph sketched over. And I already have this typed into parametric mode in the calculator. I have cosine of t cubed. Hopefully you know that that's the same thing as cos cubed of t. Just make sure the cube isn't on the inside with your t there. And I'm going to do Bubblicious here. And if I hit graph, let's see what happens. We get this really cool, like diamondish looking shape. That's pretty awesome. Okay. So if I want to find the length of this curve from 0 to 2 pi, well, there's a couple different ways that we can do this, but I think the wisest way for us to go about it is what if can I cover this up? Oh, that's pretty good actually. What if I find the length of that piece and then because of symmetry, just quadruple this length right here? Because this length should be able to be defined that if we cut this from 0 to pi over 2, then we can go ahead and determine the entire length by just multiplying that length by 4. So due to some symmetry that we see existing here, we're going to find the length from 0 to pi over 2. And in the end, multiply that by 4. All right, well, let's set this up. So those are my 2 times that we're integrating over from 0 to pi over 2. So that's going to be the definite integral from 0 to pi over 2 of the following. Well, we have to take the square root of, we have to do dx dt squared. Now, dx dt, that's going to be chain rule, right? 3 cos squared t, but times the derivative of cos. So it's going to be 3 cos squared t times negative sine t, and it's that quantity squared. Okay, so that's the derivative of x with respect to t squared plus, I think we need a bigger radical here. All right, sine cubed t would be 3 sine squared t times the derivative of sine, which is cos squared, and then dt. All right, this looks like an intimidating integral to calculate, but check this out. Let's start breaking it down. If you square the first dx dt there, that's going to be 9, and then you're going to get cos to the 4th t, and then this becomes sine squared. Plus, similarly over here, you're going to get 9 sine to the 4th cos squared. And within what we have under the radical there, there's definitely a GCF we can take out. All right, so what is that GCF I'm going to take out in the next step? I'm going to take out a 9. I could take out cos squared, and I could take out sine squared. So let's take all of that out. 9 cos squared. Sine squared is the GCF. And that leaves me with cosine squared t from the first quantity plus, if I take 9 cos squared sine squared, just a sine squared here. And as you're writing that down, you're probably jumping out of your seat like, oh, this is exciting, isn't it? Watch what happens. I mean, this is pretty complicated to start, but wait, sine squared plus cosine squared is 1. Yes, I'm shouting to an empty room. It's echoing. All right, square root of 9 cos squared sine squared. Well, this is a perfect square, so isn't that just 3 cos t sine t? That's pretty awesome. And this is an easy integral for us to calculate. You know, you can pull that 3 out front. And if we let u equal sine of t, du is cosine of t dt. Perfect. That's what's left in the integral when I pull out that 3. So therefore, it's 3 times the integral of, we'll do u du here. But we should probably change the bounds if we're now integrating with respect to u, right? So sine of 0 is 0. Sine of pi over 2 is 1. If you wanted to go back and resub in t's, you could do that. But I like doing this with respect to u. So this is going to be 3 times u squared over 2 from 0 to 1. So that's going to be 3 times a half, which is 3 halves. Okay. However, we've done this wonderful work, but don't forget from the beginning to multiply by 4. Because we decided this is only a quarter of the curve, so therefore 3 halves times 4 would be a total arc length of 6 units. Okay, and I think that's pretty neat that we have a derivation for how to find parametric arc length, and because of some symmetry in this case, we can go through this process, use some good trig identities, and in the end, I think fairly easily be able to come up with that arc length right here. Okay. So not only can we do this with arc length, but we can take our arc length concept and then extend that to what we know about surface area. Okay. So if you have arc length now defined this way, we know surface area in rectangular form for rotation about the x-axis. We would have similar formulas about the y-axis. The surface area would be now the circumference times some arc length, right? So if I were to spin this region around the x-axis, we would get this shape right here, which sort of looks like a ham of some sort. I guess it's the best way to describe it. But if you were to take a slice right here, and that slice has some length delta L right here, and then the circumference of this would help me determine the total surface area if I add up all of those slices, okay? So the circumference in general is 2 pi times the radius, where the radius might be some height y. If we're doing this with respect to x, y would equal a function f of x as a reminder. But if we're doing this with respect to y with y bounds, then this would actually just be a y here. That would stay y, okay? Well, let's talk about what this looks like with parametrics then. With parametrics, the surface area is going to be the integral from t1 to t2 if we're doing this with respect to time. And then for this piece of it, it's going to be 2 pi times the radius. That radius is defined as the Greek letter rho there, if you're not familiar with that. Not a huge deal, but we just don't want to call that x or y because it could be either of them. It depends on the equation as to what the radius is that we're using. And it depends on, I guess, the axis of rotation as well. But then it would be times that arc length parametrically with respect to t. Okay, and this would be a very similar case if we are rotating about the y-axis. So based on that, let's go ahead and take a look at what we have in our next example here. Let's find the surface area defined by rotating 5 cosine t for x and y equals 5 sine t from 0 to pi about the x-axis. Okay. So if we think about what this curve looks like from 0 to pi, and then we're going to rotate it about the x-axis, you know, if I think about what's happening when time equals 0, this is 5, and y would be 0. So it starts here. At pi over 2, this is going to be 0, but now y is 5, so then it comes up here, and I think you know where this is headed, right? And then when time equals pi, this is -5, this is 0. So of course, this is the path of a semicircle. So we're going to take that semicircle, we're going to take this curve and rotate it about the x-axis, and we're going to generate some surface area. So here's what we've got. We're going to take some slices, we're going to create some bands here. Okay, and we're going to find, for this particular band, we need to know what is the radius so we can find some circumference, okay? And then we're going to multiply that by the arc length there. All right, so surface area in general here is going to go from 0 to pi. It's going to be 2 pi times, let's get that radius out of the way right away. You know, the radius is the height to this curve. It's the y value here, so it's going to be to 5 sine t. Okay. And then we're going to multiply by the arc length, which is dx dt squared and then dy dt squared. So dx dt, the derivative of 5 cos t, is -5 sine t squared, plus derivative of 5 sine t would be 5 cos t squared dt. Okay. So now I want to start cleaning this up here. So let's see, the 2 pi and then the 5, that can come out as a 10 pi out front. So 10 pi integral from 0 to pi of sine t. And then this is going to be the square root of, let's see, 25 sine squared plus 25 cosine squared. So why don't I just actually take the 25 out of that right now and write sine squared plus cosine squared underneath. Oh, and there it is again, sine squared plus cosine squared. Isn't this just 1? So we get 1 times 25 under the radical, which is 5. All Are you okay if in this next step I have a magical now out front? 50 pi times the integral of sine t from 0 to pi. So again, this is really just a fancy 5, isn't it? Swing that out front as a scalar. So now we have the integral of sine t, which is pretty easy. This is just going to be 50 pi times negative cosine t from 0 to pi. And if we plug in those bounds, let's see, it's going to be 50 pi times cosine of pi is -1, but I'm negating that, so now we're at +1, minus, well, cosine of 0 is going to be 1, but then we're negating that, so we're subtracting -1 there. Well, 1 plus 1 is 2, so therefore we get a total answer of 100 pi is the surface area that's determined from rotating this semicircle about the x-axis. Now, wait a second though, if this is a semicircle, don't we have a formula for that? Surface area of a semicircle. Well, surface area, as it turns out, if you had a good geometry teacher back in the day, is 4 pi r squared. So 4 pi r squared, if the radius of the circle is 5, 5 squared is 25 times 4 is 100 pi. You get the same thing. Okay. So for known quantities, that we have a formula that we can go back to, that's a really nice check here. But this also goes to prove that we can, in a parametric form, use this new formula for surface area and derive the same answer. Okay. As you can see, we're going to see this example for class. So hang on to this one for next time. We're going to find the length of this curve from t equals 0 to 20. And then after we're done with that one, I'll give you some time in class to work through this practice AP question, going back to some concepts with the Taylor series here. So the nice thing about some of these next few lessons is we're still going to keep fresh with series, even though we're now in the middle of chapter 10 at this point. That is it for today, though. Have a great rest of your day.